Okay, I want to look at some of the basic concepts of digital signal processing. If you open Module 1 and get this file here, Introduction to DSP, we'll be working through that in the next 2 weeks. Open that up and scroll down past all the ImageJ installation stuff to digital imaging basics. What's the difference between an analog and a digital quantity? Now, analog quantities are continuous. They can take all values, they move between all values, whereas digital quantities can only take certain values. If you look in the textbook at figure 2.12, this in one dimension, this is one-dimensional profile here. This is continuous. It can take all values. This is digital. It can only take certain values. It can't take the values in between. Now, what are examples of analog and digital quantities? For analog quantities, temperature changes continuously. Time changes continuously. With time, we can choose to measure and display time continuously using an analog watch with the hands turned around continuously, or we can just sample time at certain intervals and give those sampled values, which is what happens in a digital watch. But time itself is continuous. Now, what about a digital quantity? These involve counting to give discrete values. Examples would be radioactivity, where you count particles, alpha particles, beta particles, or score at a soccer match, where you count goals. You can't have 2.5 goals, 2.6, they're just 1, 2, 3, 4. They're discrete values. Now, you can convert analog information to digital information by a process known as digitization. It's a two-stage process. The first is called spatial quantization, where you take samples of the continuous signal at certain points along it. This here will be distance. We're taking a sample here, a sample there, a sample there, and we're holding it until the next sample comes along. And the number of samples taken per unit distance is called the sampling rate, say the number of samples per centimeter, or the number of samples per inch, which is sometimes called the dots per inch. It's the number of samples that you take in every inch. In this case here, we're sampling at a higher rate. We're taking more samples in a certain distance. So the sampling rate is higher, and you can see the distance between the samples is smaller. This distance here between the samples, you take a sample and you hold it. This distance is the pixel size. So if you've got a high sampling rate, you end up with small pixel size. If you've got a low sampling rate, you end up with large pixels. Pixel size is the inverse of the sampling rate. And we want large sampling rates and small pixels in order to more accurately approximate the original analog signal. Now that's the first step. Spatial quantization, taking the samples, deciding on the sample rate and therefore the pixel size. The second part of it is assigning these values to binary values along this axis here. And this is known as brightness quantization or intensity quantization. So the sampled values that you get are assigned values. Let me move back to this one here. Are assigned values on this axis here, running usually from 0 to 255. Y0 to 255. Well, 0 in binary, we're using 8-bit binary usually, so we've got 8 zeros here. And the highest number you can get to with 8 bits is 8 ones, 1111, 1111, which is decimal 255. So if we assign 8 bits to each pixel, we can have numbers that range from 0 to 255. That is 256 different levels, counting the bottom one assigned black and the top one assigned white. So 256 levels ranging from 0 to 255. 256, which is 2 to the power 6. And all the values must take one of those. So if we find a value, we have to fit it onto one of these 250 discrete values, or we have to pick the closest one that we can get to. And this is what 8-bit digitization would be. If you Google Falstad Fourier and go to this site here, it opens up as this. The link is in the document also. We'll use this again later, but one simple thing I want to show you in this is if we have a sine wave and we sample it, that is, we spatially quantize it. We take samples every once in a while, equally spaced intervals along here. Then we end up with this. That's the first stage of digitization, spatial quantization. And then these values which we get here, these values have got to be assigned discrete values on this axis here, and that's called brightness quantization. And if we hit quantize, brightness quantization, we find that they're assigned just the 256 values that appear there. So there's a slight change, another approximation to the analog signal. The first one comes when we do spatial quantization, pick the pixel size, and the second one comes when we do brightness quantization. That is, we pick the number of bits per pixel, in this case 8. So if we look at image J, you open up image J and open up, we'll go to this 3, 4, 5 images, or images for 3, 4, 5, and look down. It'll be a little bit different than mine, but look down until you get Lena 256 and open her up. She's 256 by 256 pixels. She's an 8-bit image. We make her bigger by going to image scale, and we scale her up 2 times in the X direction and 2 times in the Y direction, so that then she'll become 512 by 512. We'll use bilinear interpolation. We'll talk about that later, and we'll create a new window with this bigger image. So there we have her now. She's 512 by 512 pixels. If we look at image type, still an 8-bit image, running from 0 to 255. That is 256 shades of gray. These are grayscale images with 256 shades of gray. Often what we want to do when we have an image, and we have to click on the image to make it active, we'll duplicate it. So we'll go to image, duplicate, OK, and make a second image that we can keep while we work on this one here. So I want to make this the active image and go to plugins for chapter 2. You should have these installed, and go to spatial resolution. Spatial resolution, remember, is setting the sampling rate, which determines the pixel size. So if we click on that, we see that this original image is 512 pixels by 512 pixels. We can change that to 256 by 256. And hit OK and OK again. And we get a slightly different image. You can notice it here, a jaggedness to the edge there, because we're only using 256 by 256 larger pixels now. We're merging 4 of these pixels, 2 by 2 pixels here, taking the average and forming a new pixel here and giving that average to a little block that's 2 by 2. This ImageJ doesn't update this here, but this is a 256 by 256 spatial resolution image. We go to plugins again, and we go spatial resolution, and we'll go down to 128 by 128, and we see more pixelation. That's what it's called when you can see the pixels. You can see the pixels clearly here. You can see the size of the pixels. You cannot see inside a pixel. Pixelation. We don't want to see the pixels. We don't want pixelated images. We want the pixels to be so small that we don't notice them. The pixel size is the spatial resolution. It's the smallest thing that you can see. You cannot see inside a pixel. If we look down, we can change the spatial resolution again, make the spatial resolution 64 by 64, and we see bigger pixels. So as the sampling rate goes down, the pixel size goes up. The spatial resolution of this is poor compared to this because the pixels are larger. And of course you can increase this further, and we can go down to 32 by 32 or 16 by 16. Click OK twice, and you lose the image because the pixels are so large and you can't see inside the pixel. You can't see. A pixel is just an area with a certain gray value associated with. We can see those gray values up top as we move from one pixel to another pixel. You see the position, the XY position, and you see the pixel value, 81. So you see the pixel value here is 52 at this position, and so on. You move it around, you see the position that you're at as you run from 0 to 255 or whatever we're going to, and 0 down the Y scale. We see it here, the pixel values as we move along from 0, and get that to 0, just about, and to 511. It's a 512 pixel by 512, and it runs here 0 to 511. So we've reduced the spatial resolution of this image by increasing the pixel size. Sometimes you can do an undo, but only once. So we'll get rid of that image and we'll make another duplicate of this here. We've got this duplicate image, and we'll look at chapter 2 plugins. We've looked at spatial resolution. Now we'll look at brightness resolution. We'll look at brightness resolution and change this. This is an 8-bit image. There are 256 levels, 256 gray levels from black running through to white, 256 including black and white. We can change this here to, let's say, 6 bits per pixel, where we only have 2 to the power 6 levels. We can only count from 0 to 63 with 6 bits, so 64 levels. We can do that, and not much change. Oh, try not much change, perhaps between the original and this one here. We'll go to plugins, chapter 2 plugins, brightness resolution again. Take it down to 5 bits per pixel, only 32 shades of gray. Okay, and then you start to see a subtle change. And you can see this change here on Lena's shoulder. There are little changes in gray values, and because we haven't got enough gray values over here, we can't follow them. We see this false contouring effect or posterization. And that only gets worse, of course, as we change the brightness resolution, as we reduce the brightness resolution to 4 bits per pixel. Okay, we see more false contouring, more posterization. Change it again. The brightness resolution from 4 bits, 16 shades of gray in this image. We'll just put it down to 2 bits, where there's only 2 to the power 2, 4 levels, and we see only 4 shades of gray, a lot of false contouring, and go down to the extreme. Let's take it to the extreme value where there's only 1 bit per pixel, and therefore that bit can be 0 or 1. We only get 2 levels, and we get a so-called binary image, a black-white image, although image J has used black and mid-gray, but it's essentially a black and white image. You could think about how this algorithm is being implemented. How does it change the brightness resolution from 8 bits to 7 bits to 6 bits per pixel? What's happening in the background? We know what's happening in the background here in spatial resolution. We make bigger pixels by averaging groups of the original pixels. And so in order to get a good digitized image, we want small pixels, so small that you can't see them. It means a high sampling rate. And we want many shades of gray, say 256 shades of gray, running from black to white. CT images, computed tomography images, have even more shades of gray. Generally, they use 12 or even 16 bits per pixel. So I've introduced a lot of concepts here, and you need to make sure that you understand them. If I take you back to here, I want you to go through and see that you can answer these questions. Try these questions here. We've covered most of them, maybe not this one, the point spread function, yet. Most of the others. And so this question, do you understand these terms? Well, probably not signal to noise ratio or lookup table yet, but or Nyquist, but the other terms should be familiar. So what I want you to do is skim read chapter 1 of the book. Just read it quickly, and then study chapter 2, section 4 and section 5, 2.4 and 2.5. And this should set you up to do homework 1, which is already in the assignments, and you submitted by September the 2nd.